Alright, so this is the video recapitulating lecture number 5 that we had face-to-face last week, and it tackled procedures from a hardware point of view. We're gonna see, we all know procedures when it comes to software, and we're gonna just, mention them at the very beginning of this video because they have so many names, and we're gonna go ahead and tackle them from a hardware point of view, especially with MIPS, because we're taking MIPS as an example throughout this course. First thing first, so the very last video, it was about conditions and loops, and we've seen 3 examples how to go from a high level language such as C or Java, doesn't really matter, to the hardware point of view, and we've seen how it translates into a bunch of registers if we're dealing with normal operands, and if we want to deal with the memory, well, we have to have some kind of instructions that deal with memory, and those in the case of MIPS are the loads and the store. And if we're dealing with the memory, it was the case when we had to deal with arrays. So arrays are usually larger than what's provided, the space that is provided with registers. Hence, we store them directly in memory, and we deal with them with the loads and stores using base and offsets. Right. So now, usually, when it comes to procedures from software point of view, now it's it's a better way. It's a better programming way where you can segregate logically different operations and federate them into a single, segregate the program into different operations that are federated under one or more procedures. So to get things started here, just the definition, quick definition. Well, when we have a sequence of instructions without any branches, this is what we're gonna call a basic block. This is the portion of the code that has no branches, and we had the something similar to that when we dealt with the memory, because we've seen the word block before when we talked about the memory, and it was the smallest unit that we can talk to. So this is something recurrent in different places in when it comes to computer architecture. All right, so you're gonna have a course maybe in a year or two. I just can't remember everything. Called compilers, and you're gonna see later that one of the early phases when it comes to compilation, well, it's breaking the program down into basic blocks. So you're gonna try and spread it thin, and base this spread, base it over, base it on basic blocks. So yeah, procedures. You've heard the word method before because you are Java experts. Those who've done C, they heard function. Sometimes it's called subprogram, subroutine, etc. So many names to describe the same thing, which is a procedure basically. Right, so it's a block of code that has a specific task. So logically, this is what we're gonna do if we're gonna create a procedure that, I don't know, add multiple things together and then operate on them and then return some kind of value, right? This is a specific task that is done in modular programming, notably. And from those who are taking the OS with me, breaking down a program into procedures is extremely helpful in the context of multi-threading, because we can directly map, as we said in the OS lecture, we can map procedures directly to threads. That being said, each function or each procedure normally, or generally speaking, it requires a bunch of parameters or arguments, and then we have a return value. So in hardware, how would we implement procedures? We all know how to implement procedures when it comes to software. I mean, from a software point of view, All we have to do is define the function, what the function does, and then go ahead and call that particular function from the main function or from any other function. It's so easy. Hardware wise, well, remember we're dealing with operands or the memory, and we need to start thinking of where to put the parameters, for instance. So most probably there are gonna be some registers that are dedicated for the parameters from a conventional point of view. So convention wise, we're gonna use one of the one or more of the 32 registers that are available for us with the MIPS architecture, for instance. So we need to put the parameter in a place where the procedure, once we're gonna go to that procedure, it will be able to access them. So we're gonna carefully choose those registers, and you should have flashbacks about when I started talking about MIPS, for instance, and the registers that are dedicated from a conventional point of view for arguments. And then we're gonna go ahead and go to the procedure, transfer the control to the procedure, and there's an instruction that we've also seen how to alter a normal sequential code and go somewhere else. Well, it should ring a bell, and it starts with a J. And then we'll have some kind of storage that is needed for the procedure. And again, those who are taking the OS as well, we said that systematically when we have a procedure, there's something dedicated, there's somewhere a segment in the memory that is dedicated for it, and we call that a stack. So we're going to use the same terminology here as well. And then once we're inside the procedure, we're going to execute the instructions, and then when we're done and we're ready to deliver the return value, we need to put it in a place where the subroutine or the function or the program that called the function should access it, so we can return the value, so we can be able to use it. Let's say, for example, we went from the main function to execute a particular function, function A, let's say, and then once we're done with function A, we need to go back to the main function. However, before going back, from a hardware point of view, we need to place the return, the things that we manipulated, we need to put it somewhere where it's accessible. So basically it would be one of the registers, and one or more of the registers, but the question is which one. And as per convention, there are 2 registers that are dedicated for that, namely the V registers, and for the parameters, namely the A registers. Right, so once we're done with that, we need to make sure that we're going back to the very next instruction after our function call from software point of view. So how to do that hardware wise? So we went from the main function, let's say we'd have jumped, right? So the J, remember the J type, so we jump to the procedure, and once we're done with the procedure, we need to jump back to a particular place. So we need in a way to save where to go back to. So when we're back to the main function, we're not going to the very beginning of the main function, but to the very next instruction that that follows the function call. Fair enough? And we're gonna see that in more details in today's video. So registers, the A's for registers, for arguments, because statistically speaking, most of the functions out there in most programs, well, they are maximum 4 parameters. They have maximum 4 parameters. Does this mean that we're not allowed to use other registers? As per convention, maybe not. But I mean, because all the registers of MIPS are general purpose, so theoretically we could use any of the registers. But I mean, if you want your code to be compatible and to be readable and people not get confused with it, if you're gonna use something for arguments, well, there are 4 registers dedicated for that, and those registers are A0 all the way up to A3. What if more registers are needed? Maybe we can use one of the temp registers or save registers or whatever. Probably the save registers. But statistically speaking, 4 registers are more than enough to cover the arguments of most of the functions that exist out there. 2 registers, V0 and V1, for the return values. And something important that we need to keep track of is RA. And RA is the register as per convention for the return address. So this is the way hardware knows, well, once I'm done with my function and I've loaded the return values, well, I need to go to the very next instruction in the main function, or the function that called me. So this is where I'm going to save the address of the very next instruction of the original function. Well, I'm going to save it here in the return address register. Right? So local variables could be saved in any of the S registers. As per convention, if we're going to use those, so we need to save them. Let me explain that a little bit. So imagine that the main function is using S0, and then you have a function call. So let's say in the main function, S0 has the value 1, and then the very next instruction is something that I need to go to function C, and in function C I'm executing something, and I'm using also S0. Remember, we only have 32 registers, so basically all of the program is going to share those registers. So if you're gonna use them again, we need to make sure that we're not overriding them, so the original value is still there. And if you're gonna use them, so basically you're gonna override them. So how to make sure that we can restore the original value? Well, we need to save them, save this particular one somewhere. Where am I going to save it? Well, the easiest way, the only possible way is the memory. So I'm gonna save it on the memory. Where exactly? Well, as I said, for functions, there's a dedicated place in the memory called the stack, so we're gonna save it over there, right? So to recap, if the main function is using S0 and the function that is being called is also using it, so the function that is being called needs first to save the original value of 0 inside, the one that is from the main function, and then you can override it, do whatever you like with it. And once you're done executing your function, you need to restore the original value, so when you go back to the main function, well, it has its initial value. In the example that I cited earlier, it's 1. Alright, so jump to a particular target, which is the function that I'm calling. Fair enough. This is how I transfer the control to the function. And then when I use a jump AL, that stands for AND link, so basically not only I'm jumping in an unconditional way, but also I'm saving the return address. So basically I'm saving the address to which I should return once I'm done with my function, right? So this is a one-way ticket with making sure that I still have the address of the point of origin where I transferred the control to the function. So if we have that, so this is the way to go from the main function to one of the to call any of the functions that we already defined. There should be something for the way back. What would that be? Well, all we have to do is jump back to the the value that is in a register, and in this case, so this is a jump register, JR, and this means that I'm gonna jump to whatever address is specified in register RS, and in this case, well, register RS would simply be register RA. Fair enough? So I'm jumping to a value that is inside of a register, and in case of functions, well, I need to jump back to the original caller, so the main function, the point of origin. Well, I'm gonna use whatever value I stored in using my jump and link here. Right, so I've went over and over and over about stacks. So what about stacks here? If I want to save S0, for instance, one thing that you need to understand that the stack, and should always remember that, the stack for the MIPS people, they decided for it to grow down. So each time you're going to add something to the stack, well, it will grow down. So imagine that I'm starting here and I have SP register here apparently. Well, it's some kind of pointer to tell me that where is the first free space in my stack, or where's the last stored space in my stack. It doesn't really matter. It's the roof, it's the limit of my stack. So it's pointing to the very first free space, to the top of the stack. Let's call it that way. Now, if I want to save S0, for instance, well, if my stack pointer is pointing to address 80 here, I'm gonna save only one thing, so I need to make space for one thing here. Question: So one word, a register would contain one word, 32 bits. So if I'm saving one word here, what would be the new, and the stack grows down, so basically I need to subtract something here for it to grow down. So what would be the next value once I saved S0? So once I've saved S0, I'm going to move that one word here. So what would be the value of SP, the new value of SP? Well, because we're using byte addressing, so the very next value would be 76. So I've took 4 bytes, because the word is 4 byte in MIPS, and I saved 4 bytes to be able to save my the content of S0. Fair enough? This is if I'm using S0 and if the function that called me is also using S0. Right, so this is where I'm saving it. Alright, so it's better to say that the stack pointer is always pointing to the top of the stack, right? Now, once we're done with the procedure, and the function that is currently using S0 has modified its value, and we need to go back to the point of origin using the jump register instruction that we talked about earlier. So what should we do about S0? How to restore the original value? Well, all you have to do is load what we saved earlier into S0 and transfer back the control to the main function. But we still have to do something else, because notice here we had moved the stack pointer to make space for a word, but now we restored the word here, so we should move it back. So we need to pop the stack back, so the stack pointer will be equal to 80 once I'm done my function call. Alright, so let's see an example of the way easier. So here I'm having a function. I have 2 parameters, and inside it I'm just adding the 2 parameters and putting it in a temporary, in a variable here, and then returning the result. Sure, this is not optimized, and I don't care. It's just an illustrative example so we can follow up. Fair enough? And now the questions, as usual, as we've done earlier, is we need to ask ourselves whether you're going to use the memory, we're going to use strictly registers, what are the things that I need to save on the stack, etc., and how to go back to the caller. And what's the caller? It's the function that called me. So let's see that. So remember, apparently here I'm going to use one of the registers that is being used by the main function. So the function that called me, I'm going to consider that it's the main function for now. So I need to make space growing down, remember? So whatever the original value of the SP, I need to make space for it for one word. And then I'm going to save that one word. So see, I'm using this as a base now, the stack pointer, and with the offset 0, I'm saving S0. So apparently I'm going to use S0 that is also used in the main function. Fair enough? Now I can do whatever. I can use S0 and then I can restore the values prior leaving. So let's do something here. So I need to get those. Oh, hold on. So as per convention, where do I get those? Oh yes, right. The A registers. So this is what I'm doing. I'm adding A0 to A1, putting it in S0, that is representing C here, right? So I have overridden whatever original value S0 had, but it's okay. I'm gonna restore it prior to leaving. And once I'm done that, well, I need to put the result. So see, now I need to put it in somewhere where the caller, the main function, can read it. So this is the return value, and there's, as per convention, some registers for that. Well, I'm gonna use V0. So I'm adding whatever contents I have now in S0 to 0, register 0. I'm not going to talk about that. What would be the value of 0 here? You already know. And then I'm gonna put it in V0. That's it. Now, from an operational point of view, I'm done. But I need to clean after myself because I've done some stuff here. First off, I need to, in a way or another, restore the value of SP, pop the stack, and then transfer, branch back to the main function. So I'm loading the things that I saved earlier, the only thing here that I saved earlier, popping the stack, adding 4 to it, so the stack pointer is back to the original value of it, and then I'm jumping to the content of the return address that I have. And of course, this assumes that the instruction that we called proc with, well, is a jump and link. And it is a jump and link. Alright, so caller is the one that calls the function. A callee is the function that is being called. Fair enough. And then a stack, it goes like a LIFO. So this is where I'm going to save some registers that I might be using inside my function. And what's LIFO? It's the opposite of FIFO in a way. So LIFO is the last element to be saved is the first element to be popped out. So when we say we're adding something to a stack, we're saying that we're pushing it to the stack, and then when we're gonna remove it from the stack, we say that we're popping it. And the stack pointer, as I told you, is, you know, it shows the top of the stack. Alright, so here we want to save S0, S1, S2 in a consecutive way. So let's see. So as the stack pointer is pointing to here, and then I need to make space for how many elements. Well, I want to save 3 because apparently I'm going to use them inside my function, so I need to make 3 words. 3 words. This means that because we're using byte addresses, well, we need to move 12 bytes away. So I saved S0, I saved S1, and then I saved S2. Now when I want to pop things out, well, I'm gonna pop on the last element that I put because it's a LIFO matter. So yep, so the example that we've seen till now is called the leaf procedure. Why do we call it the leaf procedure? Because after we've done a function call, that's it. We're gonna go back to the original caller, which is most probably the main function. Well, so there's no continuation. This procedure is not calling another procedure, and in this case we call those procedures non-leaf procedures. This means that the main function will call function A, and then function A will call in turn function B, or function B could in turn call function C, etc. And the very last function that calls no one but is being called last, well, this is the leaf procedure. It's like a branch and leaves, right? Like on a tree. And let's do some analysis here. So basically, the main function is calling procedure A. I'm using A0 for my argument, and I'm putting 2 in it. So and then I'm jumping and linking to procedure A. Now inside procedure A, I'm gonna call procedure B, and I'm using A0. This should ring a bell. Alright, and then I'm jumping and linking to procedure B. So there's a conflict. First off, because I'm overriding whatever I have in A0, and we've learned till now that if I'm overriding something inside of procedure, I should do something about it first. Well, I could save it on the stack and then restore it. That's why I don't lose the original value. So first off, it's about A0. But what else? Think about it for a second. So once I'm done with procedure A, I need to go back to the return address, which is the main function that is stored in RA. Once I'm done with procedure B, I need to go back to procedure A, jump and link, so it's stored also in RA. So yeah, I'm overriding stuff in RA as well. So if I'm overriding stuff in RA, well, what should I do about it? Well, I need to save it on the stack as well. So basically anything that I might be using inside of my procedure and being shared by other portions of the code, well, I need to spill it on my stack. Right? So push things up and then save them. Let's see an example of a non-leaf procedure, and that's the final example I think for today. So here I'm having the first procedure, and then the first thing that I'm doing is calling another procedure by adding 1 to the main argument, and then once I'm back, well, I'm gonna have from the original value take 1 out and then return C, and here it's just an incrementation of whatever I'm getting from here and returning it. So let's see how it goes. Everyone got that? To procedure. This is the leaf procedure and this is a non-leaf procedure. Let's start with the main function. So main function, I'm adding 4 to A0 that I'm gonna use in procedure 1, and I'm jumping and linking to procedure 1. And once I'm done with procedure 1, I have nothing else to do, so I'm gonna jump to exit. Fair enough? This is inside of my main function. Now I'm gonna imagine how proc1 goes. So yeah, I'm gonna use A0 apparently, so I need to save it. Maybe I'm gonna use also an S or something like that. Maybe I'm gonna save it. So let's check these things out. So I'm making space at least for two things, right? So -8, this means that I'm saving two words. One of them is definitely the return address because I'm going to change it. It's a non-leaf procedure, so we're aware of that. And the second one most probably is going to be the A0 that I'm using here. So that's it. So I'm saving the return address, so I will be able, once I'm done with the other procedure, to go back to the main function. And plus, because I'm using A0 to call the second function, so I need to save it as well. Its original value that has been used by the main function to call me. I mean, we could have avoided that problem just by using A1 here instead of A0. But I mean, again, we're limited. We only have 4 registers, and comes a time where we're gonna be reusing the same register. So better learn it from the get-go. Alright, so now I've done that, all I have to do is jump, add 1 to whatever value I have, and then jump to procedure 2. Right, I'm assuming that I jumped to procedure 2, and then I'm back. So once I'm back, I should go back to the very next instruction. So the very next instruction would be using the original A0, so I need to get it back. Whatever I saved here, I'm getting it back, the original one. Right? I'm taking one out of it, putting it in S0 here that I'm using for C, and moving S0 into the V register. So by moving, I mean adding 0 to whatever content of S0. I'm putting it in V0. Because I need to clean after myself, so I need to load back my return address. This is the one that will have me out, and I need to pop my stack here. And just to give you a tip, well, anything that you do here, you need to make sure that you're doing the reverse of it before leaving the procedure. Fair enough? This is the way how you can make sure that you're not making mistakes. Now that I've done that, well, all I need to do is transfer the control back to the main function throughout jump register with the value of RA, original value of RA that I popped. That's it. I'm done for procedure 1. Let's go and check what happens in procedure 2. Well, in procedure 2, I'm saving something. So most probably, it's a leaf procedure. I don't need to save the return address. I'm not calling any other function, so I'm not using the arguments registers. So most probably I'm using S0. That's why I'm making some space here. Yep, I'm saving S0 because I'm using it. Apparently I'm going to use it to represent D here. So yeah, I'm adding 1 and I'm saving it in S0, and I need to return it. So all I have to do, add it to the V0, and then load back my original S0, pop the stack, jump back to procedure 1 using the return address that happened here. Fair enough? And that's it. See you soon.